uh, it's going to be pretty interesting to see how this does play out with United Launch Alliance and Blue Origin, because they are, they're no longer going to be buying the Russian engines, and they're shifting over to the US made engines. But with the Vulcan rocket, reusing those engines is great, but a lot of it is still going to be thrown in the garbage.
Blue Origin just needs to fly something too. You know, nobody spent more billions of dollars
Yeah,
to fly nothing.
yeah,
And I don't
yeah,
doubt that they have a working thing. It's
yeah,
just, it's time to fly it and let people see. I mean, they have amazing people working for them, and
yeah.
flying New Shepard 7 times in 3 years doesn't qualify you as a rocket company.
Have you seen the videos? They're building like the fairing cones for the rocket. It feels like they have gotten a little over their skis at this point.
Yeah, it would all feel a little less outrageous if we weren't watching SpaceX, build rockets out of tinfoil and fly them in a field. Uh, and I
Yeah,
mean, you can criticize SpaceX for many things, but they're flying things,
yeah,
and seemingly spending like 10 times less money to do it than Blue Origin is to fly nothing.
yeah. Yes, it's I I don't know how anyone can make up, because I mean the new Glenn is sort of a competition to the Falcon Heavy, and when you look at some of the capabilities of the new Glenn, it's pretty astonishing. It is a clear winner for a lot of what NASA is thinking about as an intermediate step between, say, a Falcon 9 and an SLS. But it just doesn't hold a candle to what Starship is going to be capable of, especially if it actually is fully reusable. So,
Right. The whole spaceflight industry is based on the notion that Starship isn't going to work.
right,
Because if it does, they're all screwed.
yeah,
I sure wish I had a billionaire with unshakable, bottomless faith in what I was doing, because he has poured so many billions of dollars into something that isn't seemingly making any progress. Surely he has seen a lot more than we have, but still, you'd like
oh,
to see the thing fly at some point.
right, yeah. Well, it should fly next year, 2021. We should see the first flight of the New Glenn.
Well, they've been saying they're going to put people on New Shepard for
Yeah.
how many years now?
Well, how long has Virgin Galactic said they're going to be putting humans on their airplane?
Yeah, but Richard Branson basically exists just to brag. So he's kind of fulfilling his
That's
mission.
it. Your free trip on a Virgin Galactic flight just got canceled.
Yeah, well,
All right.
you gotta
Hopefully,
bite the
people
hand that feeds you once in a while.
have been saying hello. So I'm going to say hello to Bob Moeller, David Fairweather, Douglas Clausen, Harry Patrick, Johnny J, Larry King, Luke Duke, Nancy Graziano, Neil Yu, Rich Wilson, Arjone, Rose Orenstein, Sargusi, this guy, Uncle Bill Druin, and Zappan Zappan. Hey, everybody. Welcome to
Was-
Classic Weekly Space Hangout.
I have no idea what you guys were talking about. Something with rockets, but I'm so not caught up with any of that. I'm just sitting here being like, doo 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 doo. No idea.
Um,
Sounds so cool though. I wish I was up to date on like the latest rockets. Like, oh,
we should see the 20K hop for Starship
Like soon.
within the next couple of weeks. Yeah.
Yeah. So what do you think will happen first? That they manage to fly Starship to orbit, or they launch the New Glenn once in any capacity?
New Glenn. Well, no, sorry. They'll be able to fly Starship to orbit. That's not the hard part.
Right, but will they? Is the question.
Yes.
Before
Yes.
they fly New Glenn once.
Yes. So I think Starship will fly to orbit and then get obliterated as it's attempting to come back through the atmosphere. And that will go on for several years of just hunks of stainless steel raining down into Texas. And New Glenn will fly a couple of times. But it's not a fully reusable rocket.
Yeah.
So
Like, I wonder what Musk's patience will be for that, because we never really saw that with
bottomless.
with Falcon 9. Sure, they struggled to land for a while, but the thing was completing missions the whole time.
Mhm.
Starship isn't going to be able to fly any missions, or many successful missions until they can land it.
I wonder if they'll charge at a disposable rate and then attempt to recover the Starship. The first stage is the one they don't want to destroy. So the first stage, the super heavy, is going to be the one that they don't want to lose. The Starship, I'll bet you they'll be willing to sacrifice Starship after Starship to get this right. So I think it'll go Starship goes orbital and then is destroyed by the atmosphere, and then New Glenn launches, and it works fine. Like, I think it's just going to work, but it's not fully
It better
reusable.
just work. They've engineered the hell out of it.
I know. And then Starship will fly a bunch of times, and eventually, sometime 2022, maybe 2023, they'll crack the problems and it'll start landing, and then the entire rocket industry will disappear and all go into Elon Musk's pocket. I guess we should do a show. Or are we doing a show? I don't know.
We're already doing it, aren't we?
I guess so. Yeah.
We should talk about other things that I can contribute to.
Yeah, it's okay. We will get to a bunch of stuff in a second. All right.
Bonus coverage for the live people.
That's right.
Tuning in early.
All right. There's me. Here's my intro. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 28th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about sprites in Jupiter's atmosphere, water on the moon, Starlink, and the hollowed-out shell of a dwarf galaxy that the Milky Way gobbled up billions of years ago. Joining me this week on my screen, I've got Morgan Renberg. Morgan.
Hey, Fraser. Happy rockets.
Happy rockets. For people who missed it, we spent about the full 5 minutes just arguing over, before the show, arguing over whether Starship or New Glenn will be the first to work.
Answer, rockets are cool.
Rockets are cool. Answer, who knows? Rockets are cool. We've also got Kimberly Cartier. Kimberly, welcome back.
Hello. And for the record, I don't really know anything about rockets, so yay.
Pointy end goes up.
The pointing end goes up, the hot end goes down.
Hot end goes down.
And the rocket goes boom. I don't know.
I hope not. Or slowly goes boom.
It sort of does, though.
Yeah.
It really sort of does.
Yeah. And we got Chris Carr. Chris, welcome back.
Hello, I'm happy to be back for my first showing for my sophomore season.
Is this your sophomore? That's awesome. Yeah. How's everything going in you're in sort of the hot zone? How's it all going for you there?
Oh, a lot of Zoom meetings.
I've mentioned this in the past, just how wonderful this side of things has been for me as an interviewer, because everybody now deeply understands Zoom. They've got way better setups, way better lighting. I don't need to hold up my instructions anymore very often. It works out great. So yeah, no, absolutely. All right. So before we get into this week's special guest, I just want to remind everybody that if they want to be a part of the show, go to the Weekly Space Hangout crew. This is the community, the executive producers of everything that we do. They pick the guests, they organize to bring them on the show. So if there's some aspect of space and astronomy, research, science, astronauts, astronomers, anyone that you want to bring onto the show, join the Weekly Space Hangout crew. They'll make you an executive producer, and you can then reach out to anyone you want. So go to wshcrew.space. All right, let's get into this week's guest, and we've got Dr. Nathalie Cabrol from the SETI Institute. Natalie, welcome to the Weekly Space Hangout.
Thanks for having me.
All right, so I always ask, who are you? What do you do?
You
do a lot. So.
Yeah. No, I get in trouble a lot, but it's good trouble. I explore extreme environment as an astrobiologist, trying to understand how we search for life beyond our planet. And the other half of me is being director of the Carl Sagan Center for Research at the SETI Institute. So very exciting stuff and very busy. Zoomed up like everybody. We
all just live in Zoom. So let's talk about some of the projects from the research side. What are some examples of some of the projects that you've worked on?
So going back to what we said about the search for life, there are a couple of things they need to understand is what we are looking for when we're searching for life, where we should be looking for it, and how we should be looking for it. So this is what I'm trying to do in different ways. I go to extreme environments. I dive into very high lakes. I go to the Andes and try to go to places that look like Mars a long, long time ago, almost 4 billion years ago. But I am also very interested in understanding how we look for that life. And I also help building robotic experiments like the planetary lake lander, which was a prototype for a splash landing on a lake or a sea of Titan.
Oh.
And we did that in the Andes too. So looking at exploration for life in many, many different ways. And what I like is that it brings together people from the biology side, from the geoscience side, from the engineering side, the technology and planetary science. It's really fun.
We were talking about this before the show, that astrobiology is this entire field now with hundreds, thousands of people working in it. And yet, of course, the goal of finding life anywhere else than Earth still has yet to be officially, comprehensively done. And yet it feels like this field that is just exploding. There's just so much interest going in. There's so much interesting projects. I love to focus on a lot of these. What do you think is sort of bringing it to the rise? You know, you've had a chance to work on this for much of your career. Does it feel like the golden age? What's sort of causing it to be such an exciting time?
It's the perfect storm, but a good storm. It's an intellectual storm. And what's happening is that, astrobiology is connecting dots. And this is what I like to compare it to. So you are taking disciplines, many different disciplines, and you put those people together. They approach a question from so many different angles. And at the nexus of their perspective, then all of a sudden you have more questionings. And then you are trying new things. And at the same time, in the past 40, 50 years now that we've started to exploring planets, all the fields of science, and it's not only geology or biology or etc., they have been making incredible progress. It's not only planetary exploration, it's not only extreme environment, it's the way we are questioning things and the tools we have to question. Everything is just going exponentially, exploding. And so this is this convergence of intellectual approaches and technological approaches that are here for us. And we are this generation that really is opening the path. Not that, we were not having the same questions before, but we're starting to get tools that are giving us answers much faster.
It does feel like there's sort of two main parts to this, that you've got the discovery that life exists in more and more extreme environments here on Earth, places that nobody ever thought would be possible. Life kilometers below the ground, life hugging the ozone layer, life in extremely alkaline and acidic lakes and things like that. And then at the same time, we're finding those kinds of environments in other worlds. We're finding places, looks like there's some kind of salty seas underneath the ground on Mars, that there's clearly liquid on Titan, that there's all of these ice worlds with their liquid oceans underneath. Is it like partly like it's like the extremes of Earth and the environments of the rest of the solar system are starting to overlap in ways that people never anticipated before?
Yeah, you nailed it. Is that in the past few decades, we went from a definition of, how do we search for life, which was basically the habitable zone. And this is a linear distance. You have your star and you're within the habitable zone or you're outside, right? And then planetary exploration came. And then we started to understand that there are environment. You might be outside the habitable zone, but there are still environments that can be habitable. Look, Enceladus, Europa, and look at Pluto as well. Who could have thought about that? This is mind-boggling. They are so far away. So everything is changing. And not only that, but as you said, the research in extreme environment is showing us incredible things. And also life as primitive as it can be. The places where I go, we are finding microorganisms that are the same than the first one that evolved 3.5 billion years ago. They are very primitive and they correspond to other planetary environments. Something else that came that changed completely the game 10 years ago is exoplanet, the discovery of these different planetary environments. And now all of a sudden we have this gallery of new climate, of new planets, of new environment that we can model. And on top of that, you have the tool, AI, machine learning. You put evolutionary biology, you put extremophiles, extreme environment and exoplanet, and all of a sudden your brain can expand and start thinking in terms of life, not only as we know it, but also as we might not know it, and being able to map it in much more profound ways.
So based on what we know from the most extreme life here on Earth, and then the environments that have been found, what do you think is the most habitable place that's not the Earth at this point for any kind of life that, as we understand it? So if you did have the most extreme life forms on Earth could go to the most habitable places in the solar system, what do you think that crossover would be?
The icy moon, definitely the icy moon. And Mars, the thing with Mars is that obviously at the surface it's becoming a little harsh, even for the most extreme environment. Although I would say that contrary to most of my colleagues, I don't think that, if there is still life on Mars today, and I do believe it has to be there, I don't think it is that deep. I've been roaming too many extreme environments to think that life cannot adapt much closer to the surface. But what I'd say is that equally, I would say that, the icy moon and Mars, for life as we understand it, Titan is really intriguing. Titan is really intriguing. And to me, this is the lab where we are going to learn in our solar system to start searching for life as we don't know it. And there is another way to try and search for life as we don't know it, which is thinking in terms of Carol Cleland's theory of the shadow biosphere as well. So this is a theoretical tool, whereas Titan and Mars and the icy moons are real rocks, and you can play with them.
In terms of life as we don't know it, what do you think is some of the kinds of ways that we could try to search, say, a place like Titan? As you say, it sort of has all the hydrocarbons going on. It's got access to water. It's got access to energy, but it's cold. So
well, I don't think that cold is a problem, except for me right now in that room. It's very cold. But I've seen life adapt to so many things, and it's not as cold as Titan, obviously. But I had a little microorganism trapped in ice for an entire winter. We brought some of that ice to our lab, and it stayed in the fridge 6 more months before we got to it and to analyze it. And when we started thawing it, then the little zooplankton started swimming like nothing happened. Took the plane, got transported from the Andes to our fridge. So life is resilient. And I'm not talking about bacteria. I'm talking about complex microorganisms here. So I would say, cold is not something, is not a showstopper for me. As long as you meet the metabolic needs of life, it's going to function. But I think that we need to stop necessarily thinking in terms of what's familiar to us. And I think that at this point in time, astrobiology is making an interesting turn, and I really love it, because I think we had this discussion a little bit earlier in trying and defining life. The problem we do have when we are searching for life somewhere else is that we don't have a definition for life. And as I told you, I don't think we need a definition for life. A definition for life is a tool to search for something in a very specific context.
Right. You know it when you see it.
Not necessarily, but at least you are taking the steps, to, that goes back to the nature of life, but let's not talk about that now. What I think is important at this point in time in astrobiology is we're starting to think in terms of what are universal, parameters or universal evidence for life. What can be universal, not only specific to us, but universal?
Yeah.
What are the universal signature of life? what we call agnostic signatures of life. And there are also things that life does. It's not the only thing that does, but life and the cosmos has a mathematical truth to it. And so life and nature are fractal. And now, if you are looking for patterns and deviation to patterns, what else better than AI can help us do that? So astrobiology right now is exponentially developing those fields where you are searching for life with mathematics and physics and not only chemistry, although you can look for pattern and recognize this pattern through mathematics.
But it is interesting. I mean, we can see how difficult it has been. Just to confirm, I mean, there was the Mars meteorite, the Allen Hills meteorite. There's been the phosphine discovery on Venus, which I think we're about to watch that start to get dismantled. There was, of course, the Viking experiment, and there have been other things as well. And it's so hard to get an unambiguous signal that life has been found. There was a question from Visto Tutti. What instrument would be needed to unambiguously detect life? Like, obviously, if you saw a tree or some rat on Mars scamper past the camera, then you would know you found life. But for the kind of life that we're expecting, what do you think it would take to unambiguous say, okay, we found life?
That's the holy grail, right? And you're right. And you know, the more evolved that life is, the easier it's going to be. If tomorrow you have a flying saucer landing on the, the White House lawn, then it's pretty obvious. If you are finding some technosignature somewhere, it's pretty obvious. But as you go towards the transition from prebiotic chemistry to life, if that transition exists, then you have a problem. And at this point in time, we're not that good at understanding, what's an unambiguous. There isn't one that is unambiguous now. But for all the examples that you mentioned early on, Viking and the Allen Hill meteorite, and I was an extremely, I was very close friend with Dave McKay, and I discussed with him. I didn't agree with his conclusion, and we had long discussion. He took some of my sample from the Andes to go through the process because he was honest towards what he was doing. But all of these have a common thread. For Viking, for Allen Hill, for phosphine, is a lack for us to understand completely or enough of the environment of these planets or the environment of the rock or the discovery, because life and environment co-evolve, right? This is a co-evolution, which means that a planet will give you the physical and chemical conditions for life to evolve and will give you a typical kind of life, a specific kind of life. But then when life appears, then it changes everything. Look at what it did on Earth. And then you have changes in environment, life adapts. And then life releases something up in the atmosphere. And then all of a sudden you have oxygen in our atmosphere. And then everything changes again. So you need to understand the environment to at least have a background that you can deduce stuff from. And then like life creates disequilibria. These are the kind of things that we are looking for. But to tell you that we have an unambiguous signature for life today, no, we don't.
Yeah, no, I mean, we definitely don't. Otherwise, I think there wouldn't be all these arguments about it. But it really does show how difficult this process is going to be, and that I think a lot of people are waiting for that announcement that life has been found. But it's probably going to come in little bits and pieces and just by discovery after discovery, confirmation. And even the people who are working on it be like, I'm like 75% sure we found life, but I'm still not certain.
It's going to stay as, one of the hypotheses for quite some time.
Yeah.
You see what I'm referring to here. But I think that, again, by learning more and more as we're doing, how to understand the environmental background, then we're taking great strides towards making that discovery unambiguous. There is a point where you can put that much methane in an atmosphere, for instance, for it to be related to only geology. But what that does is that when you are making those discoveries, and this is what the good that came out of the Viking experiment, what good came out of that is that NASA created this integrated program so that we could understand the environmental background. We went with the Mars Global Surveyor, that was the geology, then Mars Odyssey, that was the climate. And then finally we put Spirit and Opportunity on the ground, and now Curiosity. And then again, now we have a good idea of the background, what the background is. And so we are sending Perseverance, which for the first time is somewhat going to look at biosignatures.
Right, yeah.
But it's a process.
Yeah.
I think that unless a rabbit jumps in front of the rover on Mars, it's going to be a tough one, but
Yep.
it is a very worthy one.
Oh yeah. Well, it's the most important question that humanity can possibly ask. I think it easily goes into one of the most important scientific questions that face us is, are we alone?
It is, and it's not only a scientific question, it reaches out to so many other levels, of questioning.
Yeah.
Some people are asking this question from a spiritual standpoint, from a physical, and they are not excluding of each other. But Mars is special. When I hear people saying, why do we insist with Mars? Because it's dead, it's desert. First, we don't know that it's dead, but it's definitely desert. It's the possibility we have exchanged material with Mars, and that our own heritage here on Earth is gone because of plate tectonics, because of erosion. And if we shared any sort of lineage with Mars, then those rocks that show that transition from prebiotic chemistry to life, they're still sitting somewhere on an outcrop on Mars.
Yeah.
And we are looking for a family tree maybe there.
That'd be amazing. Yeah. I mean, if there is a family tree, that means one thing. And if it's completely different, then that means something different. Either one is fascinating. So if people want to follow your work, you're the director of the Carl Sagan Center. So if people want to follow your work as well as the Carl Sagan Center, where should they go?
Well, you can go to the SETI.org, which is the website of the SETI Institute. You can also join me on Planetary Landscape on Facebook, where I'm talking with people, commenting on images or news, or trying to keep a conversation going with a little over 1.4 million people now. It's becoming a little difficult.
Keep you busy. You got to have some time for work.
Not the whole four. They are not all answering questions, but this is what I'm doing, trying to entice people, getting them interested in space and understanding how important it is to ask those questions, that they do have a societal impact. In fact, when many people think that planetary and space exploration is a waste of taxpayers' money, I think that if understood how much this exploration has an impact on their daily lives, which they don't see, they use every single day, they would change their mind.
Wonderful. Well, thank you so much for joining us on the Weekly Space Hangout. Really appreciate all of your work. You're an inspiration, and let us know, promise, when you find aliens.
We will.
Thank you so much.
You're welcome.
All right, take care.
Bye.
All right, let's move on to the news this week. Chris, I choose you. It's like a Pokemon.
Oh, great. Lovely. So
I choose you. All right.
Yes, and so I'll be talking about hollowed out shells around the galaxy. So this is a very, very recent development. I think the paper came out this week. So I think to put this discovery in context, or potential discovery in context, I think we could start out about what was the motivation for this research. So we've known for about 20 years or so about like this strange grouping of stars in the Milky Way stellar halo. And this sort of clustering it's sort of in the direction of the Virgo constellation, and so it kind of gotten the name of the as the Virgo overdensity. Mm-hmm. And there have been a lot of like sort of going back and forth about what could be causing this Virgo overdensity. And because the strange thing about it is that it has stars that are going both towards you and away from you, when usually what you expect when you find these overdensities is that they have some bulk motion in the same direction.
Right.
So the fact that you had that sort of disagreement, sort of stars moving away from you, stars moving towards you, it was a strange dynamical curiosity as to why you could have that. And so the group's research that they recently came out was building off prior work that they had published last year, which was proposing that the reason why you have this Virgo overdensity is that it's actually a hollowed out shell of an old dwarf galaxy that the Milky Way consumed 3 billion years ago.
Wow.
And actually remember this quite well because the lead author on this study, Thomas Donlan, from the Rensselaer Institute, he actually gave a talk at Columbia last year, and so when I found the article this week, it really stuck with me. And so what came out this week was sort of building on that prior research and showing not only is the Virgo overdensity a potential shell, but there are also other similar structures in the Milky Way's halo, and you get this beautiful simulation that was included in the paper. And so it sort of shows you how you can get this this multi-hollowed out shell structure from a radial merger. And so that was really sort of the major takeaway from this paper is that these radial mergers are somewhat rare for disk-like systems. And so the fact that we're seeing this in the Milky Way is really something. And I'd be happy to go into sort of the meat.
Yeah, well, I mean, I was looking at the image. I'm sort of thinking about, I mean, I know we're in the process of gobbling up, say, the Sagittarius dwarf galaxy.
Yes.
But it's a more obvious galaxy. Is that just because this one happened a lot longer ago?
Right. So I think here's where we really have to understand how different orbital properties of dwarf galaxies produces different remnants. And so if you have what you call sort of a tidal merger, which is what's happening with Sagittarius, is where you have the disk in the center and you have the dwarf galaxy orbiting on a somewhat more circular orbit like that. And so as it's spiraling into the center, it's losing material, and the material that's losing starts to trace out the arc of the orbit, and that's where you get stellar streams from.
Right. Yeah.
Yeah, and galactic dynamicists, we love stellar streams because the orbits are literally written in the stars.
Right.
And so they're a great way to sort of model. So they have great utility when you're trying to model the evolution of the system.
I mean, it's kind of like archaeology, right? Like you're looking back in the history of the Milky Way and just sort of like pulling off these strips that were once galaxies, and knowing this one hit the Milky Way, got gobbled up, then this one, and you can kind of piece back the history of the formation that built up the Milky Way as it is today.
Oh, exactly. We actually refer to ourselves as galactic archaeologists.
Yeah.
But in this case, the reason why you get sort of the shell structure rather than streams is when you have a radial merger, you can kind of think of it more like a spring, where you have the galaxy at the center, and you have the dwarf galaxy at the end of the spring, and sort of falls in and kind of oscillates back and forth as it slowly gets consumed. And so as it reaches the furthest point in its oscillation, it's shedding stars. And so it's not hard to imagine then that as it falls in and comes back, you'll have stars that are coming towards you and stars that are going away from you.
Right.
And so that's kind of the motivation for this idea that what we're actually seeing here is a remnants of a radial merger that hasn't priorly been detected.
Right. And do you think that there are more of these to be found? I mean, is the technique applicable? Was this like the brightest version and now they can just use this in other ways?
So this gets to an interesting consequence of this research, and one of the reasons why it's still very much in question whether or not this actually is a radial merger is because there is evidence of a prior radial merger in the Milky Way 8 to 10 billion years ago, and that's sort of colloquially referred to as the Gaia sausage merger.
Yes, yeah, I've heard that before.
And so sort of thinking of that is that you had one of these major radial mergers 8 to 10 billion years ago, and so one of the conclusions that the author makes here, or one of the possible consequences, is that the Gaia sausage and this radial merger that we're seeing here are actually the same event. and that
Right.
the Gaia sausage didn't happen 8 to 10 billion years ago, but that it actually happened 3 billion years ago.
Oh, interesting.
And so that's sort of like the radical like sort of interpretation of these results. I'm personally skeptical of that,
Yeah.
but it is something that we really have to consider, that these radial mergers may also be the remnants may also be lurking in the halo, as well as the streams from other mergers.
And so, I mean, are these really coming from thanks to Gaia data? Like, is Gaia what's setting off this revolution in understanding the history? It's got to have been the greatest boon to galactic archaeologists, right?
Oh yeah, oh yes, my advisor tells me every day how great.
Everyone thank Gaia, and then we'll move on. Yeah.
Yes, because Gaia has given us like such improved measurements to billions of stars in the Milky Way, that we can actually start testing our theories with present-day observations, and it's connected with these other surveys that are looking at the chemistry of stars. And so this gives you like a full like chemical kinematic picture of the Milky Way that you can then connect to your theories about the Milky Way's formation and evolution.
Yeah. It's funny, like we're still part way through Gaia, and I feel like the next release is going to be the big one. Like we're still, I mean, obviously people are still digesting the previous releases, but upcoming releases are going to have things like, oh, here's an additional 50,000 exoplanets that we didn't know about. You know, go ahead and start trying to confirm those, and not to mention all of the other data. And it's such an amazing, like really, you know, people always ask me like, you know, what's your favorite mission? I'm like, Gaia, just because of the amount of science that's been pouring out of it. I mean, you know, until James Webb or LUVOIR launches, but for now it's Gaia. Yeah. Awesome. That's fantastic news, Chris. Thank you so much. All right, Kimberly, what have you got for us?
Well, I have some sprites for you, but first I have to say you said the name. You said James Webb, which automatically pushes the launch back a month.
Oh, does it?
And adds another $100 million onto the price.
Yeah.
So
okay.
Thanks for that.
No problem.
You jinxed it.
I am post I'm post being worried about that. No longer care.
I suppose that's true.
James Webb. There.
It's not like Beetlejuice. It's not going to summon the telescope magically.
Oh, maybe that's how it works. Yeah. All right. What have you got? Science.
Science. This delves into one of my favorite new topics that I've only just started like really digging into this past year, and that is lightning on other planets. The planet in particular that I'm talking about now is Jupiter. And what's really cool about this is, you know, we've detected lightning, all sorts of lightning on Jupiter, on Saturn, on Uranus, on Earth, obviously. But it's all sort of been the standard type of lightning that we would expect, like bolts of lightning, giving off very similar signals to the type of lightning that you'd see coming off of a thunderstorm. But what was just detected by the Juno mission with its ultraviolet spectrograph was a different type of lightning that we see on Earth, and it's called a sprite, or an elf, or elves, I guess, which is a really, really horrible acronym. Don't look it up. You'll lose all your faith in astronomy.
Oh no, is it like a backronym? Is it like a bad acronym?
It's very, very bad. Don't look it up. I took like 3 lines in my notepad to write the whole acronym down.
Oh.
Anyway, the Juno mission and its ultraviolet spectrograph I was looking for auroras on Jupiter, which Jupiter has auroras, very beautiful ones, and it was looking in the ultraviolet at the auroras, and then sort of in the corner of one of its images, it saw this ultraviolet flash where there wasn't supposed to be one. And then it kept going, and it saw about 11 of these flashes over some period of time. And what was strange about these ultraviolet flashes was they weren't at quite the right frequency for normal Jupiter lightning. They weren't in the right place around, you know, this Jupiter's sphere where most of the lightning exists. And it wasn't at the right altitude for most of the traditional Jovian lightning that would come off of, you know, a storm cloud. But what it did very closely resemble was the type of flashes we see on Earth from sprites, which are sort of these many miles wide flashes of light that they take like a millisecond of light. And it's this giant sphere, like 10 to 30 miles wide at times.
Wow.
Above a thundercloud, like
Right.
many kilometers above a thundercloud that has these tendrils of lightning that face downward. So it sort of looks like a big jellyfish in the atmosphere.
Do they
a couple
reach the
milliseconds.
ground, or are they still like? Do they actually reach
They're
the
still
ground in the
pretty
way a
far up.
lightning
They're
bolt
still pretty
does?
far up.
Or are they-
I'm not sure if
Okay.
sprites generally reach the ground just because of how high in the atmosphere they normally are and how briefly they flash. Like I'm talking like millisecond flashes.
Mm-hmm.
Elves are just like sprites, just much like 10 times bigger.
Okay.
But still just as fleeting. Transient luminous events is what they are called.
And
the
why
duration of
they?
Why are they?
Yeah.
Because electrostatic builds up in the atmosphere, and
But
it needs
why
a place
above?
to
I
discharge.
guess why are they up in the atmosphere?
I don't fully understand that physics. I'm gonna be fully honest there. Why sprites exist above why it exists above thermal clouds,
Or just why they exist
I would imagine it has to do with different currents of ions in the atmosphere and the conditions that exist above a thundercloud produces the right conditions for this flash of light and the tendrils going downwards.
Right.
I mean, lightning is all about electrostatic currents. So the duration of the flash, the height, the location, the frequencies that it was observed in Jupiter's atmosphere all points to something like a sprite or like elves, which is something we've never seen on another planet before. So if Gaia is my favorite mission because it sort of kind of is, Juno comes a very close second, just for all of the new and interesting things that it brings us about Jupiter. And you know, it's tiny but fierce, this mission.
Yeah. Well, and we always talk about how like they weren't even going to put a camera on it.
Yeah, I always talk about JunoCam. This was not a JunoCam.
No.
This was not a JunoCam discovery.
This was one of the science instruments that they planned.
This is one of the actual planned science instruments, doing excellent lightning science on finding unexpected types of lightning on other planets, which is just very cool. And I think the coolest part is that this lightning might be pink or blue or some color that we don't see on Earth.
Right, because the color is defined by the chemicals in the atmosphere.
Yes.
Right.
Yeah. So on Earth, sprites are red usually. Mm-hmm. On Jupiter, they might be blue.
Oh, wow. It's interesting. They're finding auroras in more and more places in the solar system, not necessarily like what we have here or even what they have on Jupiter. They've been found on Mars, on the backside of Mars, away from the sun. A comet has even been found now with an aurora.
Yeah, the comet's not really an aurora because it's not from from a magnetic field, but it looks an awful lot like an aurora.
It's fine.
It's just very, very cool.
Yeah.
Very nice atmosphere.
We're calling it aurora. Awesome. That's very cool. All right, Morgan.
Let's talk about the moon. We want to go back.
I'm gonna resist a rant about.
Do we really want to go back? Are we sure?
We want to go back to the moon.
We want to go back, and when we go back, we want to stick around. None of these little pinky 2-3 day trips. We are going to stay. We're going to build a lunar base. There are going to be lunar vacations, all that good stuff.
Yeah.
But to have that happen, we need water. And we need more water than we can plausibly bring from Earth. We ship water to the space station. That's one thing. Getting water all the way to the moon is going to be another challenge. Fortunately, we think that there is water on the moon waiting for us. And we've thought this now for about a decade based on spacecraft observations of these permanently shadowed craters on the moon. And you peer inside these permanently shadowed craters and you see the signature of what looks like ice. But there's always been this kind of like nagging uncertainty about it because the same wavelengths of light emitted by water, which of course is H2O, are also emitted by hydroxyl. And hydroxyl, which is, think of it as alcohol, is OH. And so it's not like a full proper molecule, but it's a functional group on molecules that emits with many of the same properties.
Right.
And so we've assumed, because of the structure and the positioning of these observations in the past that what we're looking at is water, but we haven't known for sure. And we haven't also known really quite how much of it there is. And so this week, NASA shared two sort of disconnected but complementary studies about water on the moon. So let's talk first about those craters near the poles. So these are craters that are totally shadowed, and thus the temperatures in them are cold enough that the ice can survive. And we've seen these in a whole wide variety of craters. We've seen these ice signatures, but we haven't looked everywhere. And so this study used topographic maps of the moon to find all of the depressions on the surface of the moon that had the potential to be permanently shadowed based on the orientation of the moon's orbit around Earth, Earth's orbit around the sun. They did these really complicated simulations. And this is just kind of crazy. They found all of the depressions down to the size of a square centimeter that could potentially be permanently in shadow, which are places that we could potentially have ice.
Yeah.
And when you add all of that up, what you find is 40,000 square kilometers of potentially icy locations on the moon. And so that is quite a lot of ice. And it kind of expands our imagination about the locations in which these things can be. But they're all around the poles because the geometry just doesn't work to have places near the equator or even at the mid-latitudes where you don't have sunlight at least some part of the day. And so that's where the second study comes in. The second study looks for water in areas that aren't permanently shadowed. And they did this using one of our other favorite missions, which is SOFIA. And SOFIA is a big old Boeing 747 with a hole chopped in the side of it and a telescope sticking out. And they used SOFIA to make spectrographic observations of the moon. And the real critical thing here is that they used a different wavelength because SOFIA is sensitive to different wavelengths than the ones that were primarily used for these spacecraft observations. And this particular wavelength is emitted by water, but not by hydroxyl. And so if we see a signal for water, then we know it actually, honest to God, is water and not this imposter that could be tripping us up in these polar regions.
And they were, so they were thinking of like possible ways of formation. Like you could get, I think, like the solar wind impacting the surface of the moon, mixing with oxygen and forming this hydroxyl, which would give off this false signature for water.
Right. We know there's oxygen in the rocks. We know there's a lot of hydrogen in the solar wind. And when you smack a bunch of hydrogen into oxygen, once in a while, you'll create a hydroxyl atom. And those atoms, if they bounce freely on the surface, will get lost to space. But once in a while, they could sort of stumble their way into one of these permanently shadowed areas and kind of build up.
Right.
And then we go with our, big space straws to go get the water we need for our space station and find, oh boy, actually, there's nothing drinkable here.
Right.
And so they're using SOFIA and they're looking for the evidence of water in places that aren't in these permanently shadowed craters. And they find it. They actually find a tremendous amount of it spread across the polar regions, but not in the craters themselves. And, on the face of it, this is kind of weird, right?
Yeah,
the whole point is... Right. The whole point is that the sun hits the surface and warms it up too much to allow ice or liquid water to remain on the surface. And so the reasoning here is that this is water that actually isn't sort of nakedly exposed to space. Instead, this is water that is probably in vapor form and probably trapped within other compounds. So one suggested formation is you have a comet or something hits the moon, and of course it instantly vaporizes that water, but it also vaporizes the surface of the moon, and that stuff all gets mixed together. And when it starts solidifying again very quickly after the impact, some of that water gets trapped within the crystal structures of that material. They described it as sort of maybe being glass-like.
Huh.
And this process seemingly could have been quite efficient. They said you could find about 1 water bottles worth of water in every cubic meter on average of lunar soil that they found.
Right.
Which is a lot.
Yeah.
Like a water bottle per cubic meter is, I mean, you wouldn't want to like have to live by farming that, but this is not a negligible amount of water.
Right.
Which is cool. The flip side is that getting it out of that glass is probably not that easy. And so, in some ways, this is kind of like presenting us with a great opportunity and then pulling it away at the last second, because hey, you don't want to go all the way to these permanently shadowed craters and deal with these hundreds of degrees below zero temperatures to find the ice in these craters. Good news, we have water all over the moon.
Right. Just dig anywhere you want. You got water.
Dig anywhere you want and you're going to find it, but you're going to need this really complicated processing strategy to free your one bottle's worth of water from that 1 cubic meter of lunar regolith.
Like you might have to somehow grind the regolith into a powder to release the water into some kind of vapor, have some other system that's collecting the water out of it, and then some place where you're dumping all of this material overboard. Yeah, it does sound pretty
This
extreme.
is not an aquifer or something that we're going to be able to leverage, in our first few lunar missions. And so, but still, set aside the human spaceflight aspect of this, and it really does kind of reinforce this notion that the solar system is a wet place, and every time we've looked and thought someplace was dry, actually it turns out there could well be water there.
Mm-hmm.
And it just, there's this extra layer of complexity in the makeup of solar system objects that we're still sort of being surprised at every time we discover it.
Yeah, I mean, that's one of the biggest, I think the direction that things are going is that we're finding, like, even in asteroids like Bennu or like Ryugu, that there's probably large amounts of water and other volatiles just under the surface. There's probably mountains of water. I think someone was talking about Phobos, that you would easily, as you drill, if you tried to drill a base into Phobos, you would come across enough of the volatiles and water that you needed to sustain your habitat. That was thought, the entire inner solar system was thought to be bone dry, and now it turns out that you just get under the surface. And this idea of comets delivering it makes a ton of sense, that we still see comets rampaging around the solar system today. And so if they're smashing into the moon, they're delivering their water somehow.
And the nice thing about, having billions of years is that none of these processes have to be particularly efficient.
Right.
They just have to be not perfectly inefficient. And over, thousands of cometary impacts over hundreds of millions of years during the late heavy bombardment, you build up enough of a reservoir. And then if you can efficiently not lose it, then you're stuck with it forever. And we're finding that these processes turn out to work in the favor of more water in ways that we weren't really primed sort of a priori to imagine they would be.
Yeah. Yeah. Well, so we just now need some human beings to go to the moon in only 4 years and start to begin our permanent human inhabitation of the moon.
One step closer.
One step closer. All right. We've got a little more time, so let's talk a little bit about Starlink before we go.
Sure. So we've been seeing this big, just endless stream of Falcon 9s launching Starlink satellites. I think we're up to 14 operational flotillas of satellites launched into space. And finally, they've accumulated enough of a constellation that they're ready to start large-scale testing to show us how it actually works. And I think last time I was on here, so a month ago, we talked a little bit about how they were making this available for people fighting the wildfires and communities that were damaged by the wildfires in the Western US. We saw some other stories in the last month about some Native American tribes that had been given access. But now a lot more people are getting a chance to try it out because they've launched their public beta. And so if you live in relatively high northern latitudes and you're one of the lucky people who was selected, you can actually plunk down money today to receive your Starlink internet kit.
So what does it cost?
And so it costs you $500 up front. That buys you the cool space antenna to connect to the satellites. And then $100 a month. And we don't know if this is going to be their final pricing. It could be higher than this. It could be lower than this.
Yeah.
But it's not crazy, I think, is kind of
No.
the bottom line here. $100 a month is a lot for internet.
That's less than I pay for internet.
But if you're in a relatively rural area, it's probably less than you're paying, and it's vastly better. So they're saying that beta customers should expect speeds of between 50 and 150 megabits per second.
Wow.
And pings of 20 to 40 milliseconds. And now there will be brief times where the service still totally drops out.
Yeah.
So if your life is running a e-commerce site off of your home bandwidth from the middle of Nebraska, this is probably not the service for you yet.
Yes.
But it's offering something that is just sort of worlds different, orders of magnitude different than what is available to rural Americans and to rural people all over the world.
My parents have been on a waiting. I've had broadband in my city where I live for 15. The 17 years that I've lived in this city, no problem. And my parents live on a small island just off the coast of this city. And they've had just an absolutely terrible internet connection for that entire time. They were only able to get a high-speed internet connection, but they get about 1.5 megabits down and about 0.5 up. It's just barely enough to browse the web and send email. It's really hard for them to be able to watch television, etc. They're on the beta list. They can't wait to shift over to go to Starlink. It'll be a complete game changer for so many places. It's I think, on the one hand, Starlink destroying our astronomy and especially radio telescopes. On the other hand, this was one of the big unknowns that I had always had, which was what's it going to cost? Who's going to be able to get it? And so if it is regular people at $99 a month, that's pretty compelling.
And one of the key features of the beta is that there is not an NDA. And so, for the first time, really, we're going to get sort of no BS evaluations of how well it works. And that ultimately will sort of be the deciding factor about, whether this was all worth it.
Yeah.
Because if this, as we've said this a million times, if this proves to be, a reasonably priced gateway for the next billion people to get online, then you can make a solid moral argument about why it's worth sacrificing some aspects of astronomy to achieve that. If this is going to be an unreliable, finicky thing just so billionaires can get Netflix at their Jackson
on their
Hole
super yacht
ranch, then it will have been an unmitigated disaster. And we're more than one step closer to finding that out now, that real people will be able to test it at real houses in real places and share their feedback.
So again, I for a while tried to find out what it would take to get my parents better internet to service that island, and it would be in the millions of dollars. You go to the service provider, and to get the people on that island, you need an investment of millions of dollars. But now you don't need it. Now you could do things. I mean, you think about things like, as you said, there was tribes, that were getting installations. It would cost, say, $3 million to run fiber optic or cable from the nearest center to that location. But in this case, you could set up one of these terminals, set up a really good Wi-Fi transmitter, and then you could blanket your entire area in high-speed internet for the $500 cost of the receiver, plus whatever it's going to cost for your Wi-Fi transmitter. And so it's just, there's nothing else would be able to provide that level of service. So I'm hopeful, but also curse you, Elon Musk, for destroying astronomy. Yeah.
Trouble.
Yeah, I mean, we're not going to know how this all plays out. Like, I wish these regulations for what the pricing would have to be, what the service levels would have to be, what the NDA would have to be, should have been locked in from day one. And the fact that we're having to just wait and see what we get frustrates me. But
yeah, well, here we are, and at least finally we're going to know.
Yeah,
and that will be an important determining factor for policymakers in the future to figure out what to do as these kinds of networks proliferate.
For most people, it's not going to be for you. But
they're not even going to offer it to you in most people. If you live in a place where you can get 100 megabit service any other way, they're not going to give it to you. You're not. This is not for you to topple your cable provider's hegemony
as
over,
much as you hate your cable provider.
As desperately as we would all like to take our local fiefdom and burn it down. Starlink is not the answer.
Yeah.
But for the people who don't have that option,
they have no internet.
This is going to be a revelation, and it's exciting, notwithstanding all the challenges, to think about the opportunities that will enable for people to live in places that they haven't been able to live before, to have jobs and livelihoods that weren't available in those places before. And it's certainly exciting to think about the possibilities. We just have to understand the costs as well.
Yeah, and hopefully mitigate the consequences to astronomy. Don't forget about astronomy, Musk. We're watching. All right, it's time to wrap up this week's show. Morgan, you're on my screen. What are you working on? Where can people find out more?
Yeah, so come down to Fort Worth Museum of Science and History. Check out our awesome climate change exhibit, Project Planet. And if you want to see what I'm up to, you can check out my website, morganrenberg.com.
Awesome. Kimberly.
Well, people can always find me on Twitter at AstroKimCartier and on eos.org. I've been getting ready for American Geophysical Union's fall meeting, which is 3 weeks this year, all virtual, 3 weeks. Oh my gosh. You see I'm already going a little bit.
That's a whole other conversation. It's
a whole other conversation. No, it's going to be 3 weeks of really amazing science, and it's actually free for students this year because it's all virtual. So if you haven't been able to go before, this is a really great time to learn just amazing science from amazing scientists from all over the world. And I've just been getting all of my news articles ready for that meeting. It's just a lot of stuff.
Yeah. All right, Chris, what are you working on? Where can people find out more?
Well, I'm a grad student and I'm trapped inside, so I'm not doing much of anything else. But when I do exciting stuff, you can follow me on Twitter at @TheRealCCar.
Awesome. All right. How is your grad school journey going so far? How much more? When do you get your PhD?
Well, I'm the second year, so probably not
another year.
You never ask that, Fraser.
Really?
Never ask a grad student when you're done.
We manufacture PhDs.
Never.
Both of you got your PhDs thanks to this show. So, I just like to keep track of how many PhDs we've manufactured. All right. This week I've got nothing interesting to talk about. All right. Nothing I'm doing, but actually we are. So I'm just going to point you at the weekly newsletter that I'm going to be writing again on Friday. I do this every week, 25 to 30 stories. I write them all by myself, and it's like turning into like a gigantic magazine at this point. So if you haven't already, go to Universe Today.
Think about starting a website.
Yeah, I should start
all those stories on there so people can look at them out of order.
Oh, that makes sense.
Hire some staff.
Hire some staff. Sure.
Big brain ideas over here.
Yeah, you guys have really got some good ideas. I'll call it like Space Universe Now or something. All right. So but yeah, you can of course go to universetoday.com/newsletter to sign up to my newsletter. All right, and put everybody back on the screen. There we all are. Thank you, everybody, for watching us today. Thanks to the moderators. Special thanks to Nancy Graziano, of course. Every week, couldn't do this without you. All of the and our special guests. That was a fantastic interview. So we will see all of you watching next week, and I will see all of my co-hosts in some random configuration in the coming weeks and months. Stay safe, everybody. See you next week. Oh, where's my button? There it is.